So do you need to put anything onto here? So you don't need to put anything on the PDF?
This old fashioned, that is, as I said, I'm not even like that. Let's talk about the Friday lecture.
So that's the Zoom. So if anyone chats here, you'll see it straight away. Good.
Yeah, certainly can see it. So we survive.
You just, this is for the online people, but you can wear this for the room if you really want to, but the room's pretty small. Yeah, so it's up to you.
Do I need that for the room? It's recorded.
Oh, that's a good point, yeah. But you record through here.
That's happened.
So you don't have to worry about that. Is it, yeah? Yes.
You can wave at that.
You just have to sync it. You know that?
Yeah. Good.
You need to check video. Yeah. Yeah.
What are you doing now?
Just have to get they can hear you.
Good. So. Good. And this guy, I just scribble, and then I change to
make your page, and then we'll come back up at the end. Yeah. But it's the same as before. You just email, and then you just
export,
and then you just yeah. It might even be there for that's it. Good. So recording.
Thank you very much.
All right. Okay. If you do get any issues, this is our phone number. Phone number to
Good. Perfect. Thank you very much. Been a long time since I've had real live lectures, so it's great. My name is Paul Kirby. I'm a biophysicist, so my expertise is in molecular machines and dealing with such things. So thermal physics and I are friends. Julian Barengut will run the second half of the course. He's a theoretical physicist and interested in clock atomic systems. Okay, so the course will be live lectures. We will post stuff on the internet. So as of today, I've posted all my lecture notes, my handwritten scribbles from which I made the lectures. They're all there on the Moodle site. Okay, let me just give you an intro first. So this is a complex subject. The problem is that it's conceptually difficult. What this means is that unless you fight with it yourself, struggle with the concepts yourself, do the tutorials yourself, work through stuff yourself, you will not get it. In fact, doing it in one term is hard because so many concepts in it that you can get lost very quickly. So advice is that you really have to work at this as you go. Part of the conceptual difficulty is there's lots of terminology and confusion. So the central thing I want you to leave my lectures with is some understanding of entropy. Entropy is horribly misunderstood. I wouldn't say that I fully understand entropy, but I've chopped off a lot of the erroneous stuff, the misunderstandings. If I can get you guys not to misunderstand entropy, I'm succeeding. The second thing I want you to be able to do is to calculate entropy. So this is a theme in physics, shut up and calculate. Don't try and figure out what it means, just know how to calculate it in every specific example. That does not mean you understand it. That means you know how to calculate it. So if I can get to that point, I've succeeded. But entropy is complex. The advice based on all this is use a textbook. So if I speak your language, you might find the way I explain it really good. But if I do not speak your language, you will not. The good thing about textbooks is it's somebody else's vision, somebody else's approach. And you might find it more appropriate. The other thing is to have two different versions of the same subject is extremely useful. So use a textbook. So sadly, or for good, I have changed the textbook this year. So new text. So the main thing is there's tons of text, but the one I like the most at the moment is Gould and Tabachnik. And it's called Statistical and Thermal Physics. And then it's got a subtitle, something like with computational applications. And that is from Princeton Press. So I've put a schedule of my lectures, those 16 lectures, on the website, on the Moodle site, and I've indicated which chapters of Gould and Tabachnik are appropriate. There are PDFs online floating out there. Go look for one if you wish. And the book is actually quite a good book. So previous text. Is by Hock, and it's called Statistical Physics. So the details are again on the website. And the previous one before that is Carter, called classical and statistical thermodynamics. Okay, again, these are on the website. There are lots of books. People have been writing about this for about 100 years. Okay, POC I don't particularly like, but I used it in the past 3 years because my colleague who was running the course with me loved magnetism. The good news about using POC is that I've included some magnetic examples. And they're actually really useful. Carter is an older book. It's dodgy, but it covers the course. So on my lecture schedule, I have included all these three and given you chapter and verse as to where the material comes from. Okay. One other book I want to mention, it's a shadow book. It's Callan. It's just called Thermodynamics. The reason I mentioned Callan is almost illegible. I had it as a textbook when I was a student, but it's actually visionary. So the approach that Callan developed is going to be the backbone of the approach I will be using. So if you're at the top end of the class, go look at Callan. Callan is not for the faint-hearted. It's not well written, but the deep structure that I present, I believe, originally came from Mr. Callan. Okay, so I've listed a whole bunch of other textbooks on my notes. Look at them if you desire. Some are better than others. It's okay. Any questions or any of that? Yeah. Yeah, okay, I'll get, where is the microphone? Yes. Thank you. Please yell it. Is that better? Much better. Excellent. Okay, so new page. Okay. So subject divides in two halves. So the first half is thermodynamics. And the second half is statistical mechanics. So these two are different visions of the same material. If you wish, you could only study statistical mechanics and still figure everything out. And if you wish, you could only study thermal physics and figure everything out. But to get a deeper understanding, you have to connect the two, because concepts developed in thermodynamics are then translated into statistical mechanics. And without that link, the whole thing collapses. So this side is macroscopic and phenomenological. Whereas this side is microscopic and statistical. So in a sense, statistical mechanics is more fundamental. It's the basis for the phenomenological thermodynamics. But to understand what the statistical mechanics is telling you, you need the concepts from thermodynamics. So this is the link. In fact, although thermodynamics is phenomenological, ultimately it is statistical. So as you make a system smaller and smaller and smaller and smaller, the statistical properties start to appear. I work on molecular motors. These are proteins that may have 50,000 atoms. At that size, statistical fluctuations are massive. And so statistical aspects become central to understanding how they work. Okay, that's what I'm teaching. So not going to let me. So what is it about? So in a sense, why bother studying this old-fashioned phenomenological subject? Well, there are a couple of things that are really important in this. So, good, I get colors. Maybe a blue. Get more colors. Too complicated. I'll leave it alone. Oh, good. No. Okay. Okay, away. Good. It's about heat. It's about heat, first and foremost. Second, it's about all processes that occur at temperature greater than 0 Kelvin. So when you sit in the quantum mechanics class, you're studying whatever, there's an implicit assumption that this is occurring at 0 Kelvin. That's true for all parts of physics. So you're assuming the thermal effects are negligible. And this is basically untrue. The smaller it gets, the more important temperature is. And for big systems like rocks and things, you can get away with no thermal physics. But if it's happening at greater than 0 Kelvin, you need thermal physics. The next thing that is important is transformation or transduction or just plain old transfer. Of energy. So any system that takes energy from one source and moves it to a second source has to deal with thermodynamics. So again, in my game, I deal with molecular motors. Those molecular motors take chemical energy and somehow produce physical mechanical work. How do they do that? Transduction of energy, central issue. The last thing is transformation of states of matter. So basically phase transition. Anywhere where you have a phase transition occurring, you need to use thermodynamics or statistical physics. They're the tools you have to understand that. Camera has lost me, I believe. Hello, camera. Found me again. Okay, so this is the rationale. Okay. Ooh, what is this rubbish? Don't know how to get rid of it. Yeah. Goodbye. Looks like some physics. Okay, so where does it fit in physics? So I'm going to be teaching you classical thermodynamics. And it's got a twin, which is statistical physics. And what I'm going to be teaching you is a macroscopic it's statistical and phenomenological. They're the three properties there. This guy here derives thermo from statistics of underlying particles. So, in a sense, the discovery of the phenomenon of entropy in thermodynamics basically is saying, wait a minute, this stuff that I see, matter, is made up of particles. Those particles have properties, and those properties endow the system with entropy and temperature. So whenever you see this property entropy appear, it means that underneath the hood, there are particles jiggling around, and hence the statistical properties. The other thing is that it's a deeper foundation. So thermal physics is purely phenomenological. Statistical mechanics puts it on a deeper footing of the properties of the underlying matter. Okay, so all of this is ancient history. So this and this are all children of the 19th and early 20th century. A lot has happened since then. So we have non-equilibrium thermo, and we have far from equilibrium thermo. Don't want that. And StatMech. So this guy here, non-equilibrium, came roughly in the early part of the 20th century. So this is early 20th century. And it deals with systems that are close to equilibrium, but not in equilibrium. And the last guy is a modern child, so 20th century to now, and it includes biological systems, and hence my interest in it. So if I put some arrows on all this, we probably go, those two come together, they join up, and then we head this way, and then we branch off and head that way. So that is my scheme as to how this all fits together. Unfortunately, we're only going to be covering the top two areas. So literally, we're covering in this subject these two. Okay? Those two, you'd have to go and join a research lab and see what different people are doing in those spaces. Okay, so we're working in the bottom space, far from equilibrium. What more do I want to say? That's good. Doing all right. Okay. Let me throw it at you guys. Why would you bother studying this? I'm telling you it's conceptually difficult. I'm telling you it's confusing. I'm telling you it takes ages to figure out what it means. Why are you doing this? Yeah. You have to deal with it.
We don't live in zero Kelvin.
We don't live in zero Kelvin. Could you live in zero Kelvin? No. Okay, why not? Nothing happens. If you live zero Kelvin. Does nothing happen? Possibly things can happen at zero Kelvin, but not very much. Nothing complicated. Right? Any other takers? Yeah.
What can happen at zero Kelvin?
It's a very good question. I think I'm imagining a two-state system, as a theorist would. And somehow at zero Kelvin, I have external input photon, which is not at zero Kelvin, bonks it and makes it make a transition.
Would that be something that
Probably not. I don't think anything can happen at zero Kelvin. Zero Kelvin is a very strange place to be. But say again? I don't think so. But you can get very, 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 very close. People are at extremely low temperatures because they want nothing to happen. So if you have your quantum computer, you want to prod things and make them make transitions when you want it to. Actually, good question. Can a quantum computer work at zero Kelvin? Entanglement mean anything at zero Kelvin? These are all good questions. You do want low temperature because you don't want thermal fluctuations. Now, I'm half biologist. Biology absolutely requires thermal fluctuations. Molecular motor works because of thermal fluctuations. So rather than fighting against thermal fluctuations, it says, okay, I've got huge thermal fluctuations, let's use them to the max. This is why I'm interested in this bottom thing, far from equilibrium. So biological motors work because of thermal fluctuations, whereas human designed motors don't want thermal fluctuations. Thermal fluctuations are friction. Friction is bad. So it depends on your perspective, what you're trying to do. Well, I guess I've said all these things, which I've written down in the notes. Understand state transitions. And understand energy transduction. So basically anything greater than 0 Kelvin, all processes. Okay, one other thing. I think I want, if it was me, I want to understand this because I want to understand how the world works, things that I observe. And we are living in a world roughly at 300 Kelvin. And in this world at 300 Kelvin, there are a whole lot of things that are irreversible. Reason, thermal physics, statistical mechanics. And if I'm an astronomer, and I'm definitely not, they're interested in weird astronomical objects, neutron stars, etc. Why do they exist? A mixture of quantum theory and statistical mechanics. So a lot of structure in the world comes from this. Understanding the properties of materials, thermal physics, statistical mechanics. So lots of stuff. And for someone like me, if you're a nanotechnologist, this is essential because, so let me just put a second heading. This is for physicists. Straight physicist up here, and for nanotech and biophys, me. So basically at nanometer scale, statistical fluctuations dominate. Actually, let me be more specific, at nanoscale and around 300 Kelvin. This is very important, okay? And for biology, machines, essential. Okay, so if you want to understand how a molecular motor works in a cell, you need to understand statistical and thermal physics, particularly statistical mechanics. And these have macroscopic effects. Okay. You are doing physics, therefore you need mathematical tools. So let me write down what I want. So the mathematical tools you will need are not too complicated, but you have to be not frightened of them. So you need partial derivatives. And attached to that, you need partial differential equations. Okay, but they're going to be fairly simple. So another way of saying that is functions of several variables. In particular, I want first and zero order homogeneous functions. Okay, so we're going to use those. They just come out naturally in the formalism of thermal physics. We're going to use some very simple properties of mainly first order homogeneous functions, and zero order ones pop out of those when you differentiate them. I will cover this material in what I'm teaching you, so you don't panic if you don't have it. And if you really want to understand it deeply, you need Legendre transforms. Again, I will cover this, and what this gives you is an idea of conjugate variables. Okay, you will not have to do a Legendre transform, but I want you to have a sense of what it's doing, and I will do it formally and in an arm-waving way to give you a sense of why it's very important. Because the subject has been compressed into one term, not deal heavily with Legendre transforms and their consequences, but it is part of the material. Any questions or any of that? Not scared of partial derivatives, happy to swing them around and make them play and sing. Good. Okay. What more do I want to say as intro? Okay, brief history. This is really a rough history. I think it's a child of the Industrial Revolution. So that's where it starts. And because of that, there is a fetish with motors. I don't care about car engines, steam engines, any kind of, apart from molecular motors, which I love. But understanding how energy is transformed is central to an engine. And this is where we will start. So basically, energy transformation. And with this, you want efficiency. So how good can an energy transducer go? And in particular, it's about heat to work. So the realization around the time of the Industrial Revolution was that heat transfer is energy transfer. So if heat transfer is energy transfer, how much energy can I suck out of a hot object and use it to do work? And this was the question that was resolved. So the players in this are Joule, Helmholtz, etc. That's the start. What came out of this is the first law. And what first law is just conservation of energy. So surprisingly, conservation of mechanical energy had not been realized or properly stated until after conservation of energy in the thermodynamic context. Conservation of energy was first realized and figured out in thermal physics, and then people realized, in mechanics it's true as well. Okay, so somewhere along this time, a genius pops up, and this always blows my mind, Sadi Carnot. Around 1824. And somehow he stumbled into the principle about the maximum amount of work you can extract from heat. So he really discovers second law. The second law in disguise. So exists a limit to how much heat can go to work. What astonishes me with Carnot is that he had so little understanding of anything, and yet he figured this out. He used a very important method. If you're trying to discover something in physics, you're trying to solve an assignment, what is probably one of the most important tools you have, especially if you don't know very much?
Dimensional
Again?
dimensional analysis.
Even better than that. Guessing, okay? He figured the first thing out logically, but the second thing, as far as I can tell, was a guess. When you make a guess, what do you have to do then to close the circle? So guess stops being a guess and becomes physical intuition. You basically have to prove that it's true. You have to prove that it's right. And so in Sadi Carnot's case, it was effectively reductio ad absurdum. So basically, you have a principle, heat only flows from hot to cold, and then he made an argument with his Carnot cycle that if something is more efficient, heat would have to go from cold to hot. And that's absurd, and so it's proven. But it really sits on a guess, as far as I can tell. Okay, so Carnot, then comes another guy called Clausius. And Clausius is 1860s. He comes up with entropy. But entropy was already there in Carnot. Carnot had a thing called Carnot's ratio, and Carnot's ratio under certain circumstances is entropy. But Clausius identified that and labeled it such. Weird word, but that's what he did. So after that, you get Nernst and Planck. And they come up with the third law, which basically link entropy and temperature approaching 0 Kelvin. Okay. And basically, this is classical thermodynamics. Okay. What more do I want to say? Okay, so this is the thermodynamic side, Industrial Revolution through to roughly 1900-ish or so. So some of the aspects of thermodynamics, especially entropy, seem magical. What are they about? So now we move to the end of the 19th century. And end of the 19th century, do atoms exist or atoms not exist? Yeah, controversial, not controversial. It was actually controversial until the early 20th century. So there's ancient Greeks, I can't remember which ancient Greek had an atomic theory, but they remain controversial well into the early part of the 20th century. So Einstein wrote a very famous paper on Brownian motion. Why that paper was so famous was that it made a clear argument for the existence of atoms and particles, particulate thing underlying matter. It was controversial at the time. Okay? And there were lots of other things like that. So basically, around the end of the 19th century, the idea of atoms, so matter made of lumps, atoms, molecules, etc. Okay, so it's lumpy. So early in the piece, Maxwell, as in electromagnetism, he developed kinetic theory. Of gases. And then after that, you get development of that method. And so the players in this are Boltzmann and Gibbs. They're the two important people who came up with this. And this is a deeper foundation. Thermo. And it's based on statistical theory. Of ensembles. I believe the notion of an ensemble goes to Gibbs. Boltzmann is often the hero of thermodynamics, who discovered the formula for entropy in terms of subatomic particles. And he had a troubled life because no one believed what he was doing. And it ended tragically. So, early 20th. Okay, quantum mechanics really appears, yeah.
About the atoms of controversial part.
Yeah.
If we, under the quantum theory, know that everything that has momentum is a particle and a wave, can't we say that atoms don't exist, but they're just little wave packets that sometimes sound like particles?
Yeah, but they're lumpy.
Wave packets, yeah.
Yeah, they're lumped. Technically they're lumped, but there is substructure.
But it don't exist as a party that exists as a bigger.
Close your eyes, they're a party.
Below your eye.
If you're looking at them at low, an object, the lens in which you look at it will vary what you see. So even with wave particle duality, if you move to a slightly macroscopic scale, things like disappears. Not a macroscopic phenomenon. Quantum mechanics, you have Schrodinger's equation 1926. I think you have Heisenberg somewhere around the same time. How long before a fully fledged quantum statistical mechanics? Any ideas? Or a textbook appears that treats 300 pages worth of quantum statistical mechanics. Any ideas? Yeah, strangely, 1930, around 1930. Michael Tolman wrote a visionary book that basically did statistical mechanics, classical, first half, second half, about 300 pages, fully fledged quantum statistical mechanics. So it was a time when things were moving at an incredible pace in physics, roughly 1920 to 19. And I'm always blown away. These guys figured it out so quickly. So quantum stat mech around 1930. And the guy that I know who did this was Tolman at Caltech. Then you get to the mid-20th. And Onsager, Prigogine, etc. And basically irreversible far from equilibrium, and then eventually to chaos. Okay, so we're not going to cover any of that. We're going to stop at the level of Boltzmann and Gibbs. The idea of an ensemble is central to all statistical mechanics, and I believe that's a Gibbs notion. As far as I understand, I'm not a historian, but Gibbs and Boltzmann were poles apart. I don't think they knew each other. I think they worked separately. Boltzmann, emotional, took it personally, killed himself, developed it in Europe. Gibbs, American, probably religious, and really just was very matter of fact and just did stuff. And why did he do it? Because it worked. But these are the people who laid the foundations for it. Okay, that's my potted history. Is there anything else I want to say? Oh, I'm going far too slowly. Okay, I'm just enjoying myself. Okay, so let's continue for a bit longer because I have a bit longer before the next hour. Oh, good. Okay, so now we start properly. End of stories. Concepts and definitions. Classical thermodynamics. Okay, the central focus of classical thermodynamics is equilibrium states. Okay, and mainly reversible processes. Okay, so that's what I want, a reversible process between equilibrium states. when I'm talking classical thermodynamics, I talk about a system. But the system is not something in isolation. The system is in isolation, nothing's going to happen. So what do I have? I've got a system, whatever it is, and I've got surroundings. So I've divided the world into two things, system and surroundings. And because of that, I need something that separates them. And that is the boundary. So I'm going to deal with equilibrium states and reversible processes. But my states are going to be states of the system and states of the surroundings, and the processes will link these together. And because I've divided the world up into system and surroundings, I need to put it all together and say system plus surroundings equals universe. Okay, it's going to be a fictitious universe, but it means that there is nothing else outside of system plus surroundings. This is going to be my idealization in every case. Okay, so I'm way away from reality. Okay, so these are the two objects I have, system and surroundings. So types of system. Well, I can have different types of system. I can have open versus closed. And what I mean by that is that matter does or does not cross the boundary. So although I'm calling it an open system or a closed system, what I really mean is that the boundary is either permeable to matter or impermeable to matter. Equally, so matter is one thing, the other thing is energy. I can have an isolated system. And here I mean no energy exchange. Across boundary. So my two types of systems, open, closed, isolated, connected, are really not about the system per se, but they're about the nature of the boundary. Okay, but I'm going to talk about systems that are closed or open, isolated. Okay, so the boundary. What about this thing called the boundary? Well, the boundary doesn't have to be real. It can be physical or conceptual. / virtual. Okay, so if I am a thermodynamic system, I have a boundary around me. The boundary can be just a sphere of radius 1.5 meters around my center of mass. That's the boundary. There's nothing there. But I can use that as a boundary, or I can wrap myself in a plastic bag, and then I have physical boundary. Okay. But what types of boundaries do we have? So let's deal with that. Types of boundary. Wake up. Good. types of boundary. Okay, so I can have a thing called an adiabatic So what does that mean? It means permits no heat exchange. So if something is adiabatic, heat can't pass across that boundary. Now I know in quantum mechanics, the word adiabatic is used in a different sense. And in classical mechanics, it's also used in a different sense. But in thermal physics, that's what it means. So no heat exchange with surroundings. Okay, so no heat transfer. Physically, you could use a thermos flask. You could use styrofoam. Etc. Something that insulates the system. That's my adiabatic wall. The opposite of that is called a diathermal. Okay, so this one, free exchange of heat. With surroundings. Okay, so basically a heat conducting wall. So if I want to boil water, I stick it in a metal saucepan, stick it on a flame, and I have heat conduction. That one is diathermal. Okay, I'm going to use a new slide. Yeah, good, done. Okay, equilibrium states. Okay, actually just ask you guys. Yes.
The diathermal means that there is no matter exchange.
It doesn't, it's silent on matter exchange.
Oh, what about adiabatic?
Silent. Okay. I think if you have matter exchange, you will have probably cannot have all six. Yeah.
There's an adiabatic wall, does that mean it's always isolated?
Isolated means that you have no exchange of heat.
No, light.
Yeah, okay, I'm gonna light different, yes, heat. Something specific by heat, so you can have energy going across light or some other form. Any other questions?
I don't think you can carry on. I like.
Let's stick with heat. Heat is complicated. So heat has to do with thermal motion and thermal agitation. I'm blocking that. So exactly what I'm doing physically is actually wickedly complicated. Okay? And so my thermos flask is just preventing conduction and preventing convection. And if I actually make it silver, I'm also blocking out radiation. Okay? It depends to what level I want to. Okay, equilibrium states. Yeah.
You've got a question.
Oh, good. Is it possible to repeat student questions in class? We can't hear them. Yes, I'll try and do that. Okay, so the questions have been about whether a adiabatic wall allows energy to move across in the form of light or something else, as opposed to heat. But as I've defined that, it really only deals with heat. I'll continue to do that. Can anyone, is there anything in this room that is in equilibrium? If so, what? Yeah,
Maybe like the water not potable.
yeah, that's going to be close to equilibrium. So the simple answer is nothing is in equilibrium. Simple answer, nothing is reversible. So the water in your water bottle is probably very close to equilibrium. Anything else? Yeah.
Just body temperature, what? A little bit.
You're not in equilibrium. If you're in equilibrium, there's only one way you can be in equilibrium. That's dead. And not even pain, completely dead. So equilibrium is actually quite hard, yes.
The one thing about the overflows with isolated.
Yeah.
Since we now know that energy and matter are the same thing, how does that affect our definition of those?
So the question is, how does energy matter equivalence affect those definitions? We're in classical thermodynamics, so it is irrelevant, okay? But you can push things and really get down to underlying statistical mechanics, deal with issues like that, okay? But at the level we're at, it's not going to be relevant. Okay, so equilibrium is quite difficult. Actually, temperature was uniform. Is this piece of metal in equilibrium? Not at the boundary. If it's temperature of the air, it's in equilibrium. Okay, I've got to be careful. So there are different types of equilibrium. So it could be in thermal equilibrium, but it's not in equilibrium. Let me continue. So, firstly is properties. Oh, what are you doing? Oh, it's me. Uniform. So it's got to be uniform throughout the system. No gradients, no nothing. Secondly, do not change with time. So that water in the drink bottle is not changing with time as long as the temperature outside is not changing. So I guess unless acted upon by external influences. By external influences. Okay, the next one is independent of thermal history. So what is this saying about this piece of metal here? I had a chunk of steel, like I have one in front of me. What is that independent of its thermal history? Yeah.
When you say that, I should be talking about like
How it was forged. So
that would be obviously a lot higher.
okay, so not so much how it was forged, but how it was cooled. So if I take a piece of metal, molten, liquid in equilibrium at 2000 Kelvin, 3000 Kelvin. And now let it cool very, very slowly and crystallize. Whereas if I take it and drop the temperature rapidly, it'll become polycrystalline. They'll be completely different. Those two systems are way out of equilibrium, especially the polycrystalline one. If it's settled into a perfect crystal, it's probably close to equilibrium. Okay?
Are you asking if water has thermal memory?
If something has thermal memory, then it is not in equilibrium. Okay? If I remember how I was, if my current state depends on my history, I am not in equilibrium. The plastic in my glasses is not in equilibrium. The glass in those windows is not in equilibrium. They depend on their thermal history. But I'll add a caveat. It depends on what type of equilibrium. Okay? If all I'm talking about is thermal equilibrium, then if the temperature inside and outside is the same, it stays constant, those windows will be in thermal equilibrium. But in terms of the state of matter, they will not be. In terms of the state of matter. So you've got to actually subdivide equilibrium into different things. Okay, so this one is going to be important to us. I'll do a different color. It's fully described by state parameters. And I'll define them in the second half of this lecture. So if something is fully described by state parameters, then it is in an equilibrium state. That's how we know. And the final one is that if I take a closed, isolated system, then it will go to equilibrium over time. Okay? So by over time, I'm not specifying what time. So for that piece of metal to get to equilibrium, it might have to wait years of years. Very long time for it to slowly resort itself out. And it will be dependent on the temperature, how much thermal energy it has to overcome local barriers. Same with the glass. If you wait, let glass sit for 500–600 years, you can start to do some strange things like forming crystals. So time, if you wait long enough, things go to equilibrium as long as they're closed and isolated, no influence. A gas in a box will go to equilibrium rather rapidly. Okay. So that's equilibrium. Non-equilibrium states. So basically everything that we know is really not in equilibrium. At best it approximates. So a non-equilibrium state, there will exist gradients, change of time, so examples are ocean, atmosphere, anything alive, okay, you've got to be careful about one thing. Some systems are in steady state. So where you have an energy input and energy output, and what's happening in Spain looks the same as a function of time, but it's not in equilibrium. Okay? So steady state is not equilibrium. Okay. Next one. So equilibrium has to do with time. Is a closed, isolated system reaching equilibrium over time the result of entropy reaching its most likely microstate, in fact? Yes, entropy will slowly approach the equilibrium state. Come on, system, respond to me.
So does that imply that one state can push one state? Like you had that piece of steel.
Hang on. Vibe is not responding. Eek. Oh no, this would be tragic. Come on, Vibe, talk to me. I don't want to lose this. Vibe is not responding. Program has crashed entirely. Talk to me. Talk to me. me, talk to me, talk to me. I think I want to do 2 more things before finishing this. Okay, I'm going to close the app, which means all of this is lost. Ick. Okay, connecting. Enjoy. Good. So it's got that still there. How do I start again? Yeah, it's recorded. I don't know what I do now. Let's see if it puts me back there again.
You can, maybe?
New canvas, where do I see that? Ah, good. Okay, new can, oh, it did go there. Okay, new canvas. So I'm continuing. Looks like it's happy. So, last couple of things. The time to reach equilibrium depends on the system. I'm going to be very vague about it. It's called the relaxation time. And it's dependent on system and properties. So for a gas in a cylinder, it'll have to do with the speed of sound and dimensions of the cylinder. So physical processes that will get rid of fluctuation. Okay, how about we have 2-minute break, 3-minute break, and I can't even see what the time is. So have a break for a couple of minutes, then I'll continue and pick up where I'm running from.
They told me, oh, you know about.
Yeah.
Well, actually, I don't know. I just.
Maybe it's something.
Then you kind of.
Oh, yeah, I know. Oh, yeah.
Okay, let's pick it up again. So this is second half. Okay. Types of equilibrium. There are different types of equilibrium, so I can't just use the word equilibrium. I've got to specify what I mean. So I can have mechanical equilibrium. For mechanical equilibrium, say I've got, okay, I'm going to talk about gases a lot. The toy for thermodynamics. I've got a gas, I've got a boundary, I've got a pin holding it in place. I've got pressure A, pressure B, and this is in equilibrium. So if I just pull the pin out, so pop the pin out, pin is now out here. This is still PA, PB, and this guy can move. So this is non-equilibrium. And this guy will move to some other place, and you end up with PC, PC, this is equilibrium. I've got time moving that way. Okay, time, not temperature. So an example of this would be to have, I don't know, house brick. A plunger sitting in a cylinder of gas. And then I drop the brick. And I end up with the plunger squashed down and the gas compressed. Brick on it. It's compressed gas. So I start in equilibrium, I end in equilibrium, but in the middle I have non-equilibrium. So this is a process, non-equilibrium, well, this guy here is irreversible. Let me write that. Okay, but just pull the pin out and let the plunger move left and right. It's irreversible. Okay. I have to do work on the system. It's not going to move by itself. Okay, so the process is spontaneous and it goes from an equilibrium state via non-equilibrium states to new equilibrium state. It can't move backwards by itself.
So they're defining irreversible processes as processes that require work.
So the question is, am I defining irreversible processes as processes that require work to be reset? I think the simple answer is yes. Okay. No, I've got to be careful with that. There are processes that are reversible. Yeah, I think you have to do work. I've got to be, no, I can have a reversible process, a quasi-static process, where I have to do work to reset it, but I extract while it's happening. It's more subtle than that. We'll get to that. This is further along the story. Yes. Say again. Zero net, so do we define equilibrium as zero net force? Probably. It's a balance, the system is balanced. So if I'm in a can, I've got high pressure gas, the force of the cylinder inwards, the force of the gas outwards are balanced. Yes,
Reversible. It's also reversible in the small movements.
so irreversible is defined in the small universe in which we've called our system. Yes. So, and again, you have to be careful. Am I only dealing with the reversibility in my system or the reversibility of the whole universe? The valid questions, you have to think about both separately. Okay, so something might be, you have to think about both separately. Let's leave it at that. Okay, next I want to deal with is chemical equilibrium. Okay, so chemical equilibrium, and I'm going to treat it like a physicist largely. I will put a chemist definition and then just deal with a physical example. So for a chemist, you mix A plus B, and you have non-equilibrium, and you end up with A plus B will get to equilibrium to some kind of a complex. That's for a chemist. So that's equilibrium. For a physicist, they tend to deal with mixing. It's purely physical mixing, no chemistry. So I have, again, my cylinder of gas. I've got a barrier in the middle. I've got big green blobs on this side. I've got small blue ones on that side. This is in equilibrium. I then break the partition. And I still have mainly big green blobs on this side, but some of them are starting to escape, and mainly little blue blobs on this side. This is non-equilibrium. And eventually I end up at equilibrium again. I've still got the broken partition. I'm going to end up in equilibrium, and I have green blobs all over the place. And I've got little blue blobs all over the place. Okay, so this is time. So this is chemical equilibrium, where my species are equally distributed throughout the system at the end. Okay, yeah. Okay, so the question is the pendulum in a mechanical state of equilibrium? All you're doing there is transferring energy from kinetic to potential, doing nothing more, nothing less. Yeah, so I'm assuming no friction at all. So is it an equilibrium? I think it is. So a dynamic equilibrium. So a seesaw is also in equilibrium if I have equal weight from both sides. I have a non-equal weight, kaboom, it's only in equilibrium once it hits the ground. If it's up here, it's not in equilibrium. Good. Okay, so I want one more. So I've got chemical, I've got mechanical. I now need, come on, device, behave yourself. Yes, good. The last one is thermal equilibrium. So again, same game. I have box. I've got an insulating wall, styrofoam. So that's an adiabatic wall. I've got hot. I've got cold. And then I swap the wall for a diathermal wall. So this is diathermal. And this is adiabatic. So initially, I still have hot, still have cold. That's initially, and then I end up with warm. So this is again time. This is equilibrium. Equilibrium. This is non-equilibrium. Okay, so that's thermal equilibrium. So, yes.
If instead of replacing the wall with the diathermal wall and you remove it entirely, would it be thermal equilibrium or chemical equilibrium?
Can be all three.
All
So
three.
the question is, if instead of changing to a diathermal wall, I just pull it out altogether, what happens? I could have all three equilibriums, depending on exactly what my circumstances are. Let me just deal with that immediately. So, go away. Last thing I want is thermodynamic equilibrium, and that is identical to mechanical plus chemical plus thermal. So if I have all three, I have thermodynamic equilibrium, i.e. all three. Okay, so that guy is equal to all three. Okay, so that's where I want to be. Yes.
Give an example for using a food substances that involve in chemical where they reach stages and you know all chemical reactions occurring.
I've done the chemical reactions. So I can have, so the question is an example of chemical equilibrium not involving chemical reactions. So just the mixing of two different gases. I could have a cylinder full of argon, a cylinder full of neon. I connect them to two sides of a vessel and then just let them fill the vessel. And equilibrium will be a uniform mixture of helium and argon throughout the cylinder.
So if I pour some oil on top, does that give me mechanical equilibrium and not chemical equilibrium?
Okay, question is, if I pour oil on water, do I have mechanical equilibrium, not chemical equilibrium? Yes, all go and make salad dressing. Vinegar, olive oil, put in a jar, and they float on top of each other. You put it home. Pick it up, shake the hell out of it, and you will have a foam. They're all equally distributed throughout. Then put it on the bench and watch them phase separate again. It's more complicated. The equilibrium state for that system is the phase separated state. So the olive oil floating on top of the vinegar. That is the equilibrium state. Figuring that out is got to do with structure of water itself.
That is state of chemical equilibrium or just one or
That is, I believe that is chemical equilibrium. That is the final equilibrium you have. It's because you have to take all the other factors into account, not just the mixing.
so the achieving one state
Whatever the system you go to. Okay, so in fact, the foam that I create when I shake the hell out of it, that looks uniform, is far from equilibrium. It's going to phase separate. It's moving very quickly. Yes. Question is polar, non-polar things. Yes. So it's got to do with properties of water. I work on proteins. Why are proteins stable? Because of salad dressing. It's exactly the same process that water molecules form a lattice that is unstable. So they're forming hydrogen bonds between their friends and flickering between different configurations. If I stick water molecules on a layer of grease, then the hydrogen bonds are really dipole-dipole interactions, electrostatic effect. And if the dipoles point towards the grease, there's a massive energy penalty for having a dipole pointing towards something that is hydrophobic. So instead, they stay in a planar lattice. They move from a flickering 3D lattice to a flickering 2D lattice, which is a massive restriction. It's a very low entropy state, and they don't like to do that. So you end up with effectively a surface tension where they try and avoid, minimize the surface interface. And so in the salad dressing, the minimal interface is to separate them completely, whereas the foam is a massive interface. For my lab, we work with proteins. The protein is a long wiggly chain. It's greasy. The best thing for it to do is to fold up into a compact, well-defined 3D structure, stabilized at the same entropic effect. Okay. Okay, so we've moved very slowly through lecture 1 because I'm just going slow, and this is now effectively lecture 2. So, and it's a continuation effectively. So, describing equilibrium states. Okay, so I need a toy system. The first toy system, simplest, is going to be a homogeneous fluid. Because it's simple and because the relaxation time is short, whereas something like a chunk of iron has a horribly slow relaxation time at room temperature. Not such a good system, too complicated. Okay, so if I have a homogeneous fluid at equilibrium, I need to describe it. And what I said before is that it's at equilibrium when it's completely described by its state variables. So unfortunately, state variables depend on what you're looking at, what your system is. I've chosen homogeneous fluid. So I have state variables for homogeneous fluid. They're going to be simple. Okay. So what is a state variable? I'm going to define it later. State variable is it's a property whose differential is exact. Okay, I'm not going to define that now. If you know what I'm talking about, good, but I'll describe this later. We will come to that. Okay, so we will get to that. Homogeneous fluid. We've had 3 types of equilibrium: mechanical, chemical, thermal. What are going to be the state parameters for each of those equilibria? State parameters to describe the mechanics of a fluid, homogeneous. How would you describe it? How would you, if I said, here's some fluid, your water bottle, for example. Volume, good. What else? Pressure. I'm going to say pressure, volume. Chemical. This one's harder. How do you describe it? Chemical. Number of particles. Good. What else? This one you won't guess. Chemical potential. Okay, so it's chemical potential, whatever that is. And number of particles. And the last one is thermal. Yeah. 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 So it's again temperature and entropy. I'm going to use this. Am I missing anything? Overall, sorry. I've got U, I'm going to call it the internal energy. Those parameters are all I need. So U is equivalent to E. But in old-fashioned thermodynamics, they call it U. In the textbook, they call it E. And actually, in fact, in both textbooks, they call it E. Okay, so for a homogeneous fluid, that is all I need to know about it in terms of thermodynamics. If I'm going to do chemistry, I need to know that it's argon and not sodium. But in terms of thermodynamics, I don't care. That's all I need to understand it. Good. Okay, so now I'm going to do something. Look at doubling system. So I take one system in equilibrium. And it's an equilibrium. So I've got a box. There it is. And I've got energy, volume, pressure, entropy, temperature, number of particles, chemical potential. And I now make two identical copies. Okay, two identical copies. Put them next to each other. Okay, there they are. And then I remove okay, so this system is already, oops. Oh, yes, there it is. Already in equilibrium because the systems were identical since two subsystems are identical. Okay, so it's exactly the same. So this system is going to have properties U dashed, V dashed, P dashed, S dashed, T dashed, N dashed, mu dashed. So now I take these one at a time. So I can say that V dashed, the volume of the big system, is equal to 2 times the initial volume when I added two systems together. But the pressure stays the same. Number of particles in the final system is 2 times the original number of particles. But chemically, nothing has happened. So the chemical potential is the same. And I'm going to just state this boldly. The entropy of the new system is twice the original entropy. But temperature dashed equals temperature. So this observation is quite important. It says that there are 2 types of state parameters. Okay. So I can partition the state parameters into two families that are not the same. I can make them look the same, but they actually aren't the same. They stay not the same. Okay. No idea what time of day it is. Leave that there. Yeah, I've got my telefonino there will tell me what the time is. Good. Please, 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 the gods. Okay. This usually is better than this. Okay, so I call the first type of state parameters extensive parameters. Extensive parameters. These are additive on combination of subsystems in equilibrium. The systems must be in equilibrium, otherwise all chaos breaks loose. So actually the one I missed out, total energy is equal to the sum of the individual energies. Okay, total volume is equal to the sum of the individual volumes, and total number of particles, sum of the individual number of particles, and total entropy, sum of the individual entropies. Okay, so these are extensive parameters. So they depend on the extent of the system, the size of the system. And the other type of parameter is the intensive parameter. So the intensive parameters remain unchanged. So these remain unchanged. When systems in equilibrium are combined. Okay, so these intensive parameters, they are the temperature, pressure, and the chemical potential. Okay, so I've got two types of parameters for this simple fluid system: intensive and extensive. And I can't morph between them. They really are different, fundamentally different. Slow, slow, slow. Good. So what I get is conjugate pairs. So because I have different types of equilibrium, the parameters pair off. I can write, oops, not like that. The extensive, intensive, and I get volume goes with pressure, number of particles goes with chemical potential, and entropy goes with temperature. Okay, they're my pairs. Have you seen something like this before in other areas of physics? Parameters and linked to each other. Yeah. So someone said velocity momentum. No, not really. That's not up here. Yeah.
Standard model.
Yeah, standard model is a good place. Where else? Simpler, simpler. Position and momentum, someone said. Where? Classical mechanics. So in classical mechanics, you get pairings. So similar, like classical mechanics. So you get, there you get Q linked with P. So this is generalized coordinate and generalized momentum. What is the transformation between the two? Pairs them together. Legendre transform. Okay, so we're getting some of these secrets coming out. Oh, this is Legendre. Where else do you see this pairing? Apart from classical mechanics. Quantum mechanics. So also quantum mechanics. So you get pairings, energy and time, position, and momentum. The other way around. What's the transform in this case? No. X, momentum space, position space. Fourier. Okay, what we'll see when we come down to it later is that the transformation in the case of thermodynamics is Legendre. Well, Legendre. Okay. So there is deep structure in physics. Things, the fact that we see the same pattern in quantum, in classical mechanics, in thermal is not an accident. Yes. Yes. We'll get to that. So there are there are a large number of formulations of thermodynamics. One is the energy perspective, the other one is the entropy perspective. So once you've chosen your perspective, the other parameter goes into the table. So I'm choosing an energy perspective, and you're getting that. If I chose an entropy perspective, you'd have a different table, and energy be in there, not entropy. But we'll get to that coming. Okay, so these are fundamental things that you can't mess with. But people doing thermodynamics like to mess with things to make things more confusing. Okay, so let me deal with this right away. I hate this, but it's used. Specific values. So the parameters remain extensive. They do not change their character. They still have the same pairings, but people like to remove the size dependence. So remove size dependence of extensive parameters. Okay, so specific value is equal to value of extensive divided by the size of system. Okay, so you can do, yes. Yes, about to do that. Okay, so I can do this size equals mass. So then I get V equals volume and little v. This is where bad handwriting isn't so good. Little v is equal to specific volume. Okay, so it now is no longer size dependent, which is nice and useful, but it blurs a fundamental property. Okay, but I can also do the following. I can say there exists molar specific values, where in this case, size equals number of moles. Okay, I'll define a mole later. A mole is a measure of the number of particles using Avogadro's number. And so in this case, I get volume and molar specific volume and little v again. So lowercase means specific. But as I said, there are many ways of defining specific because they all depend on what your measure of size is. And the two commonly used ones are mass and number of moles. Okay. Good. So we have to now describe an equilibrium state. Okay, I'm going to do this in a formal fashion. Formalism is painful, but if you embrace it, you'll find that it actually makes your life really simple. The formal approach is to say that there exists a fundamental equation. And the fundamental equation is that U, internal energy, is a function of entropy, volume, number of particles of species 1, number of particles of species R. Okay? So this is my formal fundamental equation. That this thing exists. That's all. So what it's saying in English is that energy is a function of the extensive parameters. So no intensive parameters. And there's one extra property that it has, which is magic, that it is first order homogeneous. So this formal structure is actually extremely powerful because what you'll find in thermal physics is there are millions of equations. And someone like me who doesn't have a brilliant memory scratches their head, was it this is the partial derivative of that, or that is the partial derivative of this, or what? Formal structure, you can derive it all from that equation. So this is called my energy representation. Okay, so that's my energy representation. That. But as I promised, you can do something perverse and say, or equivalently. And it's absolutely equivalent. There is no difference. I can say that instead of that, I can say that entropy is equal to a function of the extensive parameters. So I'm assuming a bunch of components here. It looks exactly the same as the energy representation. And then I can say that in English, entropy is a function of extensive parameters. Okay, and surprise, surprise, it is first order homogeneous. And this is the entropy representation. Okay. So I'm not going to deal with entropy representation at the moment. I'm going to say return later. Okay, so this is why I had that mismatch. So I did not have a partner for energy. I could have instead not had a partner for entropy. It depends on my perspective. So just a couple more words and I'll finish. So these fundamental equations provide a complete description of my equilibrium states. But fundamental equation not easy to discover. Okay, so if I could write down a fundamental equation for whatever my system is, I would have all of its thermodynamic properties in one equation. I could derive everything else from that equation. So in my part, thermal physics, we will aim to get at least 2 fundamental equations, maybe 3, from which you can derive all properties. That will be hard work. In the second half of this subject, where Julian picks up, you then find a thing called the partition function, which has the same role. From that, you derive everything, all properties. Okay, that's the goal. Okay, see you guys tomorrow. Yes, question. Come and ask me, I think. Okay, good. Good to have a live class again. Hello. System on halfway. So I've got 2 versions. It's slow, actually. I don't remember it being. It was adding pages. Send. Send. I did remember. Don't know how much. Send it.
Physics lab. They send you Zoom, okay?
Okay, so it's gone, and I just said.